Good evening, morning, or afternoon, depending on where you are joining us from today. Our talk today is engineering computational design and in the democratization of building. I am your chair, Ashley Catcher, and I'm just going to go through some housekeeping and a few reminders for you all. Please, at any point during the presentation, please ask a question. You can ask a question at any time. We'll probably address those at the end. There's no need to wait until the end to ask a question. You can do that any time. The speaker profiles for today's lecture are to the right of the slides, which you can access via your Workcast interface. If there are any technical issues, for example, poor video or audio or something similar, and perhaps slides aren't advancing or something, please refresh the browser in the first instance. That usually solves the problem. However, there is also a check connection button directly underneath the slideshow, and you can also chat with technical support via that link if required. The recording for this webinar will be available in the next few weeks and will be made available on the iStruct website. A quick copyright notice. To the institution's best knowledge, copyright permission has been provided for all material shown, and this broadcast is therefore presented in all good faith. If the copyright holder believes permission has not been forthcoming, then the relevant item will be removed, or by agreement and appropriate acknowledgement provided to accompany the lecture. Right, now we can get down to today's talk, titled Engineering Computational Design in the Democratization of Building. This is part of our computational design technical lecture repertoire, which we have on the institutional website. So there's lots of resources there, which you should be able to find. And I'll introduce today's speaker, Stephen Melville, current director at Format Engineers. In his current role, Stephen leads engineers delivering complex structures and installations. He's aided by cutting-edge digital tools, verve, and imagination. Formerly a director at Whitby Bird Engineers and then a design director at Ramboll UK. He has been a member of the Bristol Urban Design Forum and a member of the 2013 RIBA Awards panel. He is also an esteemed member of the Digital Workflows and Computational Design panel, which I manage at the institution. Having published several papers about digital design and engineering and architecture, Stephen regularly lectures and critiques at architecture schools across the world. So you're in the company of a very esteemed experts in digital engineering. I will be your chair. My name is Ashley Catcher. I'm one of the senior engineers here at the iStruct, responsible primarily for digital engineering. And with that, I shall pass on to Stephen.
Ashley, thank you very much. I blush, and I'd echo the good evening to everybody, or good morning, or good afternoon. I'll start my presentation. Share that. Can you see that, Ashley?
Yes, that seems to be okay. If you start the presentation, that should be right.
Good. Okay, and this is, in some senses, a part 2 or even part 3 of a series that I've given, or other people have given, into the application of computational design to buildings, to works of art, to structures. And we've tended to concentrate very much on the fancy project, the project which is very much in the public eye, the sort of thing that's in websites, Instagram, Zine, etc., which is fine. But I think that my talk will talk about the application of the techniques that we've learned in the democratization of building. Now, I'll talk about what democratization means in a second. But just to set the scene, I'll talk about democratization as a bit about us, very short bit about us, don't worry. I'll talk about some of the tools that they used. I'll talk about some of the complex projects. But then on the meat of this is about the grounded digital projects and how the tools and techniques that we developed, or people have developed, or the worldwide community of open source software writers have pulled together, which enables people from very varied backgrounds to produce and build some amazing projects. So I hate, we just talked about this here, I hate text in presentations, but the gist is that digital design techniques are blurring the lines, the traditional lines of scope in engineering design, or we believe they are, but they allow less experienced client bodies to erect structures, usually because they're too challenging or too costly. Our contention is that elements of the build can be broken into easy to handle lightweight components. Complex forms, and this is something I'll talk about in a second, can be split into easily fabricatable, simple ones, but with the same end result. And as I said, not only do complex, funky, design type structures benefit from this approach, but also more and more traditional typologies of building. And our contention is this is seen as a democratization of building. And this is all fine, but I think what it will need is a slight mindset change in engineering, possibly, in a skill set. We need to invest in possibly different skills. And there are good examples and there are bad examples, which I shall show you. Quick about us, former engineers. We've been going since 2014. We're very lucky that we've worked with people across the world, some really amazing artists and architects doing some incredible projects. I won't harp on too much about us. We have a small office, small presence in Paris now because we love working abroad. And our headquarters is here in Bath. So, democratization, one definition is the action of making something accessible to everyone, or the democratization of information through technology, which is from the online Encyclopedia Britannica. So the important thing here is the action of making something accessible to everyone. So to set the scene a bit further, we pulled together the flowchart of frustration. Now, this is possibly my own unique frustration, or it may be a frustration shared by many people. But to start, you start a project, stage 0 to 2. You have ideas, you investigate lots of ideas. It's all great fun. Stage 3, you develop the detail. You become at one with the design. Now, at that stage, you often find that a project will go for costing, for example. And it doesn't matter who costs it or what organization or what background, but there are many examples where people will say, "Oh, it's too complicated. It's we haven't really explained your ideas. It's too complicated. And you have to abandon the idea and start over," which is a waste of time, a waste of money. But actually, if you go past that stage, to stage 4, you then have a deep familiarity with design. At that stage, you hand over your baby to a contractor. Oops. So the contractor, here are some of our, I suppose, pet peeves. A poor contractor, will spend time relearning design. He'll replicate any 3D model that you've pulled together. There'll be questions. There'll be the inevitable wait for answers. We'll spend ages checking the contractor's model. You'll get comments such as, "I don't have Rhino, can I have PDFs, please?" Which is a waste of time and a waste of money. You get the same. It's too complicated. You have to abandon the idea and start over again. So, and then once you've gone through all those hurdles, even if you manage to convince somebody with the sheer force of will that this is buildable and it is possible, you get to build it. But then you get the further complication on some projects where people say, "But I'm not a contractor. I'm a self-build, or we're only students, or I have very little money." So there are all sorts of hurdles where the traditional way of doing things slightly falls down. The traditional way of engineers producing information, handing it over, and then expecting a contractor then to absorb that very quickly these days, and then to produce fabrication information which reflects your design intent. So, yeah, that's why we think democratization of building from the application of technology, where the pitfalls that you see later on in the design process can be ironed out. Now, I'll start by talking, as I said, about some more funky digital projects, which explain some of the concepts, get those out of the way. So one project we were involved with last year, this is the Tay Whale for an artist called Lee Simmons. This is in Dundee, opposite the Victoria and Albert Museum in Dundee. And these, I should say, are examples of projects where you're working for a client body that does have money. You're working for a contractor who is au fait with some of these techniques. So these, I wouldn't say that they're no expense spared projects, but these are the projects, they're sort of the big profile, or high profile design projects. So in the case of the Tay Whale, we used computational techniques to design every single connection automatically. So we were able to check all the connections to make sure there were no weird combinations of stresses. And then we're able to output that information as a series of cutting files for the contractor. And this is, something which is, it's definitely beyond the scope of many engineering projects. So you can see how that looked in fabrication. So it's quite a very complicated project. Another example of a complicated project where techniques that have been learned, which then feed into the everyday, that enable this democratization, was a project we were lucky enough to be involved with for the Queen's Jubilee last year, the Tree of Trees for designer Thomas Heatherwick, where you've got this fantastic, it was the beacon. So it was one of the, I think it was the primary beacon across the country, which was lit by the Queen, went around the country, and then the Tree of Trees was lit up at the end. So, it was a very fast-paced project. It involved, again, lots of computational techniques to actually, A, prove it stood up in the time, but B, enable us to produce the information that the contractor could build with very quickly. So we produced all the cutting files. Again, so we produced the 3D elements from our model that the contractor then used to actually cut the elements that went into the structure. There's the fabrication, all well. And in this great example where you have to do this sort of thing sometimes, we think, and we're quite prepared to do this sort of things, when the deadlines are extremely tight. Another example of well, again, not budget is no expense, but a project where you have a certain budget and a certain experienced contractor, but which is still extremely difficult to build, where we learned a lot, was Goodwood Festival of Speed in 2022, so no, year before last actually, which has the proud boast of being the world's largest, or the world's longest 10-secretary cantilever. And we had a matter of 3 months to actually come up with a design and build it. So, the full array of digital techniques we use, again, every single connection was designed automatically within one computer script. All the fabrication drawings were exported by us from our 3D model, again using a single computer script, all of which saved the contractor a huge amount of time. Every plate element was labeled and automatically exported. Every cable, again, was labeled and then automatically exported to the contractor. So, these are all techniques that we've really got a handle of, I think, which are absolutely necessary in the design and delivery of some of these quite complicated projects. So there's been a real investment in computational design. It really kind of pays off from that respect. And then just a quick description about some of the tools that we use. I mean, the ubiquitous one is the 3D modeling software Rhino with the parametric modeling plugin Grasshopper. And this has pretty much become the I suppose, the common language of engineering computational design. There are people out there who hold other platforms do an equally good job. They may or may not be right, but this is, I suppose, the common platform that allows us to develop 3D models, to plug in real-world physics, to plug in nesting software for CNC cutters, to manipulate geometry to make it simpler, to include structural analysis within the model to get instant feedback of how things react when you make changes to geometry. So if those of you who haven't delved into the world of Rhino and Grasshopper, I recommend you do, because it's initially quite overwhelming world, but it's one which does actually pay off. The advent of relatively cheap and cheerful CNC cutting machinery or simple laser cutting. Ashley and I were talking about this before this presentation about how easy it is now to get 3D printing CNC cutting on a small scale that people could actually use to produce viable, useful elements of a structure. So part of our role is then to say, how can we take the design that we produce to make it into small elements that the man down the street in the warehouse who has a CNC cutter can produce? And then you assemble those elements into what could be quite a complicated or unusual structure. So it's embracing the maker's movement, the small scale local manufacturing. I talked about nesting. So nesting means that we can take elements from design and put them on the sheets, and then we can send it to the CNC chap, and the CNC chap can produce elements himself, and then we can literally take them to site, and we can assemble them ourselves. Augmented reality is a goodie, actually. I will show you a couple of examples later on where we've used augmented reality, and this is an application by Australian developers Phologram, which works with a Microsoft HoloLens or an iPad to actually give you a real-world view of the structure you're trying to assemble in actual space, so you can see how it relates to the real world. And this is a photograph. This isn't a corporate photograph by Phologram. This is actually this is a photograph that we took of us testing the fit of the Goodwood Festival of Speed project in the real world. Because if you're trying to build what is reputedly the world's longest 10-security cantilever, you can't tell very easily if just cable A go over tube B, over tube C. It's like building a jigsaw in 3D empty space. So having augmented reality was absolutely crucial to getting this built. So the advent of tools such as augmented reality has really helped, we think, the democratization process. A slightly obscure diagram. I'll show you what this means in a second. So essentially it means using, again, the power of digital modeling and computational techniques to take surfaces which, in this case, double curved on the left, and the pattern shows the degree of curvature, how we can split it into simple flat elements that represent that double curvature that do not require, for example, the services of a shipyard or a boat builder to make a complex three-dimensional form, but can be split into simple parts, again, that the chap down the road in his CNC cutter can produce, and then we can bend them about one axis and we fit them together, and the shape of the pieces mean they come together in a way which really quite accurately represents the double curved surface. So this was an actual project that we were working on for the Qatar World Cup. Excuse me. So the architect's original intention was this double curved surface at the back of the structure, where it became obvious that the budget was too low and the time we had was too short to go out to a Dutch shipbuilder, for example, to procure double curved plates. So how can we split that double curved surface into flat strips, or strips that can be bent about one axis, which will then pull together of a pretty good representation of the original three-dimensional form. That was the final structure. We're still trying to get photographs at the back, which is the really kind of the funky sculptural part. But it made the difference between this building, this being built or not. So again, these are all quite. This is an example of a quite sort of well-funded project. But again, it's an example of how it wouldn't have been possible to do this very interesting double curve geometry if we hadn't been able to prove it could be done for a relatively low budget. We did the same thing for a work of art in Marble Arch in London, where we took the artist's original intent, this being an artist called Lee Simmons, of double curving stainless steel plates which whooshed out to the ground in a sort of plant-like form. But the original was too costly. It couldn't have been built. It was double curving on those plates, super expensive. So again, we've broken everything down into single curved elements cut from flat sheet. So again, made difference between it being built or not being built. So, and then these are all, I suppose, those are all the sort of as I said, the kind of funky, exciting projects that have the big budgets. But I think what I'm more interested in is the grounded digital projects. How you really take this idea of democratization a step further. So the community can build their own projects. The self-builder can build his or her own projects. So I think this is the meat of my presentation. This is the meat of what we think is democratization. So to show this in action, I'll go for a series of projects, if I may. Some very quick examples, recent examples. This is Westonbirt Arboretum with architect Piers Taylor, where, again, it's complex form. It's elements which are bent and steam bent, and then the community comes together, and then in the community, the local schools, local action groups came together to actually help build this structure. So, but the guidance they were given to build the structure and the elements themselves were all split into simple steps and simple components using our 3D models and the tools we had. So, a non-experienced, non-professional contractor could contribute to the build of this project. So we were in charge of producing those elements, or collaborating in producing those elements. That built on the work of a smaller scale project a couple of years ago at the University of West of England, where a relatively funky three-dimensional curved shell form was designed by the architecture students for their end of year show, but they only had a limited budget, a very small budget. So they could afford a saw, they could afford some bolts, and they could afford some 6mm ply, only in flat strips. But we were able to develop software which broke down that surface, that curved surface. I think I've got the slide, into those flat strips, which when bent and pulled together and then connected together with the bolts would form this really interesting double curved surface. So they were able to do this for the end of year show. It was tremendously successful. It went a bit saggy after a few months, but it's not meant to be up for a few months. But it's a great example of what you can do with the budget if you're prepared to do a little bit more as engineers, work with the digital tools you have. We are working with a very enlightened concrete contractor in the west of England. I should say he's not necessarily a concrete contractor's not a fair description. He's actually a waste to energy supplier who owns a concrete company who's looking to develop concrete shells around his waste to energy plant in order to house workshops or production facilities or growing tomatoes or whatever, which use the spare heat from the waste to energy plant. So as a prototype for one of the concrete shells, we've worked with him defining literally clay molds from the ground that make the shell, and using augmented reality to set up the reinforcement in the shell. So although he owns a concrete contractor, the concrete contractor is a very traditional organization. It's used to beams and columns and slabs. So presented with a series of concrete shells, it's a massive learning process for them. So, being able to set up the model in augmented reality to show them where the reinforcement is. This was also reinforced with a textile reinforcement to show them where the textile reinforcement should go. And before that, to show them how to shape the clay, the earth clay mold that makes this shell was a fantastic learning experience for us and for them. And they were able to do things they weren't able to do before. And it goes back, again, to my flowchart of frustration, where if we just handed this to a contractor and then said, okay, Mr. Contractor, you develop your own 3D model, you work out how to build this, they would have really struggled. They may even have failed. So by developing these prototypes, the client contractor is now confident enough to commission much larger scale versions, which are hopefully being built this year. So that's a snapshot of some more grounded projects. I was a little bit more controversial and go from examples of good projects and bad projects, because I think the flowchart of frustrations all very well, and going out and pushing scope as an engineer is all very well, but actually there are some bad outcomes to this, or there can be some bad outcomes to this, and there are some things to watch out for, some things that we've learned along the way. So there are some good examples and some bad examples. And I'll do this as a series of projects, again, because I think that this is best illustrated by real-world projects. Now, I talked about grounded projects. This is a typical grounded project. This is an extension to a house. Admittedly, it's for a member of the aristocracy in a very expensive village somewhere in the southwest, but it's an extension to a house. Now, the architect wanted some quite unusual angles. It was very difficult to actually deliver the elements for the build through a very tight series of alleyways behind the site. So all had to be split into small components, and also the contract was held to a very tight budget. So the approach, so there's a rear view of the extension. So the approach was to break it down into a series of frames, a series of hybrid plain sawn timber plywood portal frames, which were then clad in a more conventional timber frame. We developed the 3D model. The 3D model was an output from our analysis, actually, so that we developed this into a solid 3D model. We then generated the cutting patterns for the ply elements that sheathe the outsides of the portal frames. And then we gave the contractor a set of instructions of how to put this together. And this was, I think this is a good example. So there was a contractor. We didn't have the frustration at stage 5 of someone saying, I don't have any money, I'm not a contractor, I'm just a student. There was a contractor, but he was able to get this built extremely quickly because we were working with him, going further than the traditional scope for an engineer. There's a picture of it being built. Another example, one that I may have used before in presentations, but it's a good example of democracy, also in some ways the ultimate example of democratization and of building in a social sense, was this, which is a central temple for Burning Man in 2018, a structure called Galaxia by architect Arthur Mamumeni. I don't know if people are aware of the Burning Man festival, but people come across the world, they take lots of drugs and hang out and take all their clothes off and run around naked, as far as I can tell. And but it's a spiritual space, and you're meant to leave the desert untouched. And there isn't the traditional, again, contractors and people with huge amounts of machinery and plant helping you build these things. You've got to build them yourselves. So this tremendous structure, which is 50 meters clear span, spiraling tent-like structure, had to be built with literally inexperienced volunteer labor. So we went for an exercise of really splitting this down to quite simple elements, which is triangles, prefabricated triangles which could be connected together. Really, what could they produce in a cutting shop without a contractor leaning over them for help? So really simple triangles which are connected together in a simple way. We did loads of engineering optimization, which split it into different elements and different sizes in order to reduce the material, sort of thing we like doing. Actually, in this case, it was a bit useless because it meant that the elements were all different. So a better approach was to use as fewer possible different sizes, have more repetition, so it was easier to build. So we ended up with literally just 2 sizes of timber that arranged in the best way we could. I don't know about that. So yeah, fabrication started, and this is the desert, and you can see the concept of the triangles bolted together. They built the banana trusses, and this was some of the few pieces of kit they did have these long spiraling banana trusses, and they did it. So this was volunteer labor. This was architecture students. These were people from Google. These were people from Boeing. People who hadn't had any building experience, but able to build this tremendous structure. People left dedications to loved ones, messages. It's a very spiritual space. You can see the top part of the structure is built first. Maybe they should have used some experienced contractors at this stage, but they did it. So here's the team that did it. So this is the ultimate example of social building. Looks tremendous. Looked tremendous. The inside looked amazing as well. There was a great spiritual space. And I say looked a lot because the story is it took us months to design it. It took them a month to build it. And it was up for 4 or 5 days, and then they burnt it, leaving no trace. So it was something which made a mark, but not a permanent one upon the desert. Another example, I'll rattle off a few good examples, and I'll talk about the bad examples. This is steampunk central structure for the Architecture Biennale in Estonia. Fantastic swirling interlocking structure. That was the original architect's vision. It's a bunch of architects from the Bartlett School of Architecture who teamed up with the same augmented reality people I talked about before, Phologram from Australia. So it was their kind of joint design. So there's all the normal 3D modeling and structural analysis. But what was really clear is this couldn't be built. Again, it couldn't be built by a contractor because there was no budget for a contractor. It couldn't be built by a contractor because it was too unusual for a conventional contractor to understand. So the way it was built was using one of these primarily. This is a Microsoft HoloLens. So this is an augmented reality set, which flips over your head, and you can see the real world in relation to the 3D model. So you can see what you're trying to achieve when you fabricate something in relation to the real world. So here's an example of that. So here's an example of the timbers which made up the structure, which needed to be steam bent. Here's them being steam bent and pulled into the right position. And that kind of greeny yellow shape is essentially what they're trying to achieve. So the guy with the hologram can say, no, pull left, hologram, rather, can pull left, pull right to match what they're trying to achieve. And they use the same system on site. So they're able to build this, what element goes where, use the system to great effect. There's excuse me, an example of what somebody could see as they were building it. And they did it. And this would have been impossible any other way, I think. So it was a tremendous use of technology, tremendous use of computation, and it was democratic again. And this was built by the architects themselves for a very limited budget. An example of a picture. And this has led on to other projects. So I mentioned the concrete shells that we're developing with a contractor energy supplier in the southwest. This is one of the shells. And as I said in the prototype, what they want to do is set out the shell, the mold, the clay mold, and the reinforcement. Here's the reinforcement pattern using the augmented reality system. Another more everyday project, this was a contemporary house in the southwest called Park Cottage. It's up for an RIBA award soon, so we're hoping it gets one, obviously. The centerpiece was this reciprocal Zollinger roof. So it's an oak Zollinger roof of very limited length members which interlock to make a robust roof structure. Now, some of the comments that we had when we were first showing this to the contractor along the lines of, why don't you build a steel frame and just hang the timber from the steel frame? And we said, well, no, but that's not what we're trying to do. This structure is, and yeah, it's a robust structure in its own right. We don't need to hang it. So the way we're able to demonstrate to the contractor that this was possible by taking on the responsibility ourselves as engineers in doing the CNC cutting file generation for the members, the CNC cutting for the plywood panels, which sheathe the roof. So, you know, I said we developed a full 3D model. All the elements were modeled by us. All the plywood cutting patterns were generated by us, and this is one of the bad aspects. It's got the world's worst nesting into panels here, complete waste in some ways of plywood, mostly due to the architect's insistence of all the grain lining up in the same direction of the plywood. So it was a very inefficient way of nesting onto plywood sheets. But we did all that. We protested, but we did it. It was part fabricated off-site, brought to site, crane in position. It all fitted, and it looks fantastic. Couple more examples, good and bad. I've talked about this one before, but this leads on to a different project. This is a timber cabin in the Arctic Circle for our architects' spin architecture. This was built by the community. Again, the community had little money. These are two walking cabins that the local walking association wanted to commission, but they couldn't afford a contractor, so they wanted to build it themselves. That's one of the mountain peaks in the Arctic Circle that one of the things is built on. Again, this is about computation in the service of democratic building. There was one computer script which generated everything from the panelization geometry to the screw locations to the structure analysis, was all done in one model. The structure was broken down into flat cross-laminated, small flat cross-laminated timber panels. So these guys, this is the community, were able to actually get them cut themselves and then literally take them to site and build it themselves. So fueled with just cake and enthusiasm, these guys built the first cabin, I think, a week. And I think they built the second one in 2 or 3 days. So it was a pretty quick and efficient process. And this led to a second cabin, actually. This was more a research project. This was for as an island in a fjord in Norway, which is rarely visited by people. And it's a very special island where any works of architecture have to be very, very heavily scrutinized by the community and signed off. So the intent was to build a really interesting form that worked almost like a pebble, a giant pebble in the landscape. So we're adopting the same techniques as we did for the Arctic Circle cabin of simple, flat, cross-laminated timber panels all linked together. Again, we did the panelization ourselves, we did all structuralization, the structural analysis ourselves, all that stuff. Our model was then fed into, in this case, there was a CNC contractor who used our model to export his cutting files. There was a sequence of erection that was then set up from that one model. And it was built by a bunch of architect students and the architect himself. But it looks brilliant. And this is a slightly fuzzy slide. I really couldn't get any better images of this. But what this is saying was one of the learning processes of this was we set out all the screws But eventually they found they literally could not put the screws in after all. The thing was so rigid that in their view there was no point putting more screws in. But some of the angles and some of the lengths of screws that we specified were actually impractical when it came to the real world environment. So there's a sort of learning process here of knowing how much people can do and how practical it is to actually plug things together, and then feeding that back into the design process, which is quite interesting. And that's the final result. I thought fantastic. Again, pebble in the landscape. View from the inside. Just a couple more, and I'm done. This was for an Austrian company called Neuschnee, whose ambition is to produce clean energy snow machines. And they asked the local architecture department in Innsbruck to do a design for them that would house their snow machine. And then, if they were convinced, they would commission it to be built. So, working with, that is the architect himself. So he's actually climbing up and screwing in the last panels. That was the site, unbelievable site near Innsbruck, very remote. The architect's original vision, or the working with the students, was using tensioned and bent elements to create a form. It was all hands-on. This is all hands-on. So the cutting of the timber was done locally, and this is our guys. This is Marco, an ex-employee now, actually holding up pieces of timber and measuring deflection just to get a sense of what were the properties of the timber, and then literal testing of the elements when they were fabricated in a shop. And they were mostly fabricated by the architect himself, who was a very hands-on guy. It was then built again with students and volunteer labour. I always like the picture of it not clad. And it was clad, it was finished, and there's Marco being interviewed by Austrian TV. I think one more example where things went a little bit awry this is quite an old structure that we were involved with 10, 12 years ago, called Creod in London Docklands. And again, the architect wanted to develop this himself. He had this vision in these slightly movable, transportable pavilions, reciprocal timber pavilions. The whole thing was 3D modeled. All the connections, everything was in place. It was brilliant in theory. All the pieces were then delivered from the CNC cutting chap. They used, in this case, some reasonably sophisticated machinery. But I don't know if you can see that, but the connections at the end of the timber, every single one was wrong. So every single connection was in the wrong place. And it was all due to the drill bit in the machine being worn and out of alignment. And the architect, in this instance, had to do some extremely fast groveling in order to get the timber guy to donate more timber and the CNC cutting guy to cut more timber. But they pulled it off. But again, this just shows that you can do all this preparation, but the fantastic machinery at the end can still let you down. And this is definitely the last example I have, both good and bad, I think wrapped up in one. This is a small residential development sort of house that is one of our earliest projects, actually, but it's still actually being built. It's being built by a self-builder. The biggest feature, I suppose, is the roof. So the roof is a 4-way reciprocal timber roof. We should be fed up of reciprocals by now, but we decided to at least one more 4-way reciprocal roof, where the elements were pretty simple Curto beams that he could organize the CNC cutting himself. We did the full 3D model, all the elements labeled, exported, all cut. There was all sorts of testing and test fitting, and it's taken years to build, not for any fault in the design. It's just that it's become apparent that the client, the self builder, is, I suppose, in this instance, a reciprocal structure is not an easy one to get your head around. So he's taken him a while to get his head around. He had to enlist or external help to help him. So for him, it's been a real tough learning process to actually, as much as we can do, as much as we can pull together cutting patterns and instructions and do test fits, for him, it is actually proved to be quite a complicated undertaking. So there are some good sides to the democratization of building via computational design, but I think we need to be aware that if we go down this route, there's still human beings at the end who have to build it. And I think that's the end of my talk. Thank you for listening.
Wonderful, Stephen. Thank you very much. We do have a couple of questions, well, about 6 actually. So, while we answer those, I'll just jump onto camera, and if you could do the same, please, Stephen. I have to apologise. The sun's gone down in the time that it's taken me to do the talk, so I'll just have to pop the light on. There we are. Sorry about that. Thank you very much. Absolutely astonishing, some of the structures that you've created there. They remind me of often sort of sci-fi visions of the future, effectively. So it's quite interesting in that sense. It's very inspirational in that sense, I think. Now, so we've got a few questions, but primarily sort of, I suppose, in sort of 2 categories. One in sort of like the methodology, and one in sort of more, I suppose, sort of technical aspect, I would suppose. The first 2 are sorry, please do continue to ask questions if you have any. So I'll ask the first one now. The bending active structures and the reciprocal structures. So of course, bending active structures rely on the on sort of the curvature and the sort of almost like a containment force to actually pull together the structure. And the reciprocal structures, my understanding, is that they have a circular load path, effectively. Like they each rely on each other.
Yeah.
You seem to use those a lot. So my question is, what are the robustness qualities of them? Because of course, a bending active structure, if you lose some of that, say some of the sort of tension force, effectively, if you lose some of that, then does it result in a cascade of failures? And likewise with a reciprocal structure, what happens if you were to lose a member, for example?
Okay, good question. Partly it's about containment. Partly it's about the right application. So I think there are probably instances where you wouldn't use a bent active structure, for example, where a temporary structure is a great example of where you could get away with that. But I suppose it's in a sort of robust containment. Maybe it's a perimeter structure which does constrain it. Maybe it's an element of redundancy where, if I don't want to use the word over design, but the elements themselves have a bit of capacity. It's all about thorough checks into creep and material properties. It's all about simulation. And we got to the point where one of the ways that we can gain confidence in how they act, for example, was helping in the development of software to actually simulate bent active structures. So we have a tool set within Grasshopper, K2 engineering, that simulates bent active structures. So we can look at the forces. It's not, I think some of the early ones we did was kind of not, I wouldn't say guesswork, but it was a kind of first principles engineering, hand calculations, and you're never quite sure, and you do some testing and it validates what you've done. But that inspired us to actually make it a more robust physical simulation by writing our own software. So to part answer your question, you have to go the extra mile.
So actually, funnily enough, that answers one of our viewers, Cameron. His his question was exactly that. Actually, with your structural models being so complex, do you ever perform any hand calculations for simpler analytical
Oh,
models?
absolutely.
Verification?
This is a very important point, that you have to break down what you're doing into simple steps that you can calculate by hand. So rather than throwing everything into the black box of the computer, I think one of the questions is, what software do you use? So most often, for example, we would start with Karamba, structural analysis plugin for Grasshopper. But that's great, but it is the proverbial black box, and you put information in, you get a result, but you need to be confident the result's right. So you break it into small steps. You look at the reaction forces by hand. You calculate some elements by hand. It's all about breaking it into small steps and gaining confidence. But we also then check it independently. So we'll take it from Karamba, for example, and do an alternate model in GSA, Oasis GSA, to check it and then see how the results correlate.
Stephen, you're preempting a lot of the questions here, because the next one is, what software do you use for structural analysis? And I think you've just answered that effectively.
I can see the questions popping up.
There we go. That might be why then. I've got another question here from a gentleman named Tony. Apart from the architectural inputs in relation to visual delight, or I suppose I would call architectural whimsy sometimes, in general, who else defines the design briefs for these sorts of projects? Are there any sort of employers' requirements, other stakeholder requirements in relation to design codes, fire safety, etc.? And actually, this meshes with something else I was thinking about. How do you get building control as well to sign off on some of these structures?
Yeah, well, I think we have, and if you say, for example, you take the Tay whale, the giant whale that we designed opposite the Victorian Albert Museum in Dundee, that was all signed off by the local authority. And again, the way you do it is, I suppose you've got to break it into, it looks complicated, there is a lot going on, but you need to break it into super simple steps that people can understand, not because they're thick, but you can't present all that information to somebody in one go and expect them to understand it. So you need to break it into small, logical steps. And we always say we're still engineers, after all. So we're not in the business of putting information into a computer, getting a result, and then packaging it up and sending it on. It's all about interrogating what you've done and then presenting what you've done in a logical, simple, understandable way.
I think it's very important to be able to sort of understand how to communicate what you've designed. I suppose in that sense, I feel like a lot of your examples that you've given in the talk today have been focused on not necessarily even sort of perhaps all the technical design aspects, because of course there's software for that, there are techniques, there are things available for that, but really communicating the design intent and the manufacturing intent to other parties effectively. So in that sense, does the manufacturing and the construction itself, do you think that often governs what you do in terms of effectively that's a stakeholder, and they impose parts of the brief on you effectively?
Oh, absolutely. And I think that, again, I can bore you of all the particular hang-ups I have, but one of the hang-ups I have is people who say, oh, we do the concept design and we hand the concept design on to other people. But I think, and that's rubbish. I think unless you've worked with a contractor and you understand the constraints, and the constraints could be angles of plates that you can get a weld into. It can be the size of elements you can put in a CNC cutter, or what are the practical aspects of the things we're designing. Unless you've learned those, you can't then feed those back into the design process. So what we're trying to do all the time is, the design process involves steps in building. So there are no horribles. It can't be built. There's none of this horrible surprise where, oh my god, it can't be built. Even though you've explained it, even though you've designed something which is amazing and split it into simple bits, it can't actually be built. I mean, one example of that was the peanut-shaped CLT cabin we did in Norway, where it was great up to a point. We produced the information that could be CNC cut, and they did all that. And we gave them all the screw locations, the length of screws, but they couldn't probably get in the last third of the screws because the angles they were screwing in, the space they had, and they left them. And then a whole bunch of architecture students clambering along top of this thing, far in excess of probably what it was designed for. But we now know, having done that, for example, take a very critical approach about screw locations and how you screw things together, and so that gets fed into the design process.
Yeah, of course, it's a perennial problem with connections, isn't it? It's the actual access to get in there effectively. So I'm sure there are a few more than a couple of steel workers out there who understand that pain, to be honest.
I'm sure there are.
We have an additional question from Wajahat, and I think this sort of ties into sort of more general aspects of some of your work. They're asking for a example on transportation, highways, structural, that sort of thing, in terms of infrastructure, I suppose. But of course, primarily yours are your projects tend to be architect or artist driven. Now, how generalizable are your methods into, say, if you wanted to go to a motorway gantry or some sort of infrastructure bridge or something? So how easy is it to generalize some of the things you do?
Well, I think very much. And I think I did this, I think I gave a similar talk a year or two ago about how these techniques could be applied to the everyday. And it's something that we're pushing. And the analogy, I suppose, is the corny analogy is you develop the Formula One car, and the Formula One car, the technology gets spun into everyday cars. So we're trying to do that. I'll give you 3 examples of structures we're working on at the moment. We're working on a footbridge, quite a long span footbridge that will hopefully have one of the lowest embodied energies that has been built for a footbridge, hopefully. And I mean, it's a complicated structure. I can't say it's democratization of structures because it's been built for a corporate, a national body by a well-known steel fabricator. But we've used digital tools again to refine the design to its absolute limit. So it's quite a simple design in some respects, but it's super refined in terms of the angles of the members and the size of the members and distribution of members. Well, one of your questions was, do we use artificial intelligence? Well, on that structure, we did. So there were the computer script included routines to automatically move members around into configurations that were most efficient, learn from that, pick a good solution, change that solution. So again, it's literally evolving design. So there's that. We're working on an aircraft hangar in France at the moment, which is huge. And in some ways, it's quite a standard structure, but we've been able to manipulate the form of the standard structure. So it's literally a bit more wibbly wobbly, but wibbly wobbly gives it immense stiffness. And immense stiffness means we can reduce the weight of the steel in the structure. So again, these are not everyday grounded structures. So I didn't use those as examples, but it shows, I think you need to start thinking about how we can roll out this stuff into the everyday. Absolutely.
And in that sense, again, you're preempting many of the questions. Of course, you just mentioned the AI aspect and sort of using those designs. What advice would you give to young structural engineers looking to work on these sorts of things? So of course, technology is always rapidly improving, and so would you focus on technology, or would you focus perhaps more on sort of the engineering, I hate to say it, nuts and bolts?
Well, that's actually, in some ways, that's a difficult question, because look at it from the perspective of how would we value an employee. So if somebody was sending a CV to us, I think we'd love to see people have, I suppose, enthusiasm or knowledge of the digital design technique. So learning Rhino, Grasshopper, parametric modeling, scripting, all those things. So that will definitely stand you in good stead. But it is also knowing about the nuts and bolts as well. So it's joining the nuts and bolts with the technology. So, we also like people who've done the nuts and bolts. So we employ people who haven't done the technology but have done the nuts and bolts. And they meet the people who've done the technology but not the nuts and bolts, and they combine to super engineer.
Well, so, do you look for those super engineers, or do you simply have a collaborative working environment between specialists of different types and then some interpolation in between?
No, well, they've all gone home, bar one. And he should shut his ears now. But I think they're all super engineers. No, we do want people to actually absorb digital design techniques, because the opportunities for using them to refine structures. And as I said, I think I said the same thing to you before this talk. There's too much talk of it being a fetish or a style, etc. No, for us, it's all about these are tools, and these are tools to design great structures. I could equally use a pen, for example, if that's the appropriate tool for the job. And these just are amazing tools to produce amazing things in an efficient way. But you still need to be a good engineer. So the advice would be, get familiar with Rhino, Grasshopper. It's also nice if people have an appreciation of the history of engineering, because things repeat itself. So you look at the work of Nervi, and it'd be like Gaudi, Fraiotto, etc. A lot of what we're doing is actually digital representations of what they were doing 50 years ago.
Yeah, with the soap bottle, soap bubbles,
absolutely.
and various other tools.
Absolutely.
We're just using computational design tools.
Yeah.
There is actually we did a series about the year before last, and it finished last year, about Philippe Bloch's work, for example, on the digital graphics, computational graphic statics. These techniques are centuries old in comparison to perhaps even some of the, for example, Nervi or Fraiotto, but they're coming back. As you said, they're coming back sort of full circle. So I suppose the history and the sort of structural forms and topologies, I suppose, is quite an interesting one, I think, because people have been working on those for quite some time.
Oh, I mean, absolutely. I mean, the discussion could be endless. The company that we found is called Format. The reason it's called Format is the play of form and matter. I'm not sure I've ever admitted that in public before. It's form and matter. So the form is, it's the be all and end all. You start with the form. How can you manipulate the form to make the structure more efficient? And then you can start talking about the bits which make the form afterwards. So form, hugely important.
Yeah. And I think that's probably where a lot of the interest in geometry and the sort of the fantastic magical structures comes from, because from geometry a lot of the time the form will dictate sort of perhaps material or usage or the overall feeling of the structure, I think.
Absolutely.
I am going to just have a look through another question. There are two questions which are probably quite similar. Do you use CFD, and how do you choose the best options with regards to, say, adjusting parameters and such?
Do we use
They're
CFD?
not that similar, sorry, apologies, but they're similar.
Yeah. No problem. Do we use CFD? Yes. We have our own software that does CFD, which is, I mean, again, I mean, the Tay whale is one example I can think of where, how you work out the wind load on something as complicated as that is tremendously difficult if you're using the code. So we use CFD to understand what the wind pressures were likely to be, and then use those as a guide to interpret the code. So we use CFD quite a lot. Big buildings. I talked about the aircraft hangar in France, for example. We're doing some CFD studies on that at the moment to see what happens if there are two aircraft hangars, one next to another. So yes, we do use CFD.
With regards to the interaction, with regards to the interaction between the two structures and the sort of channeling of wind and such, right? Okay.
Yeah. You have to remind me of the second question.
Oh, it was it was with regards to picking the best option, so to speak, especially when you're churning through these. I suppose what people call it is optioneering, don't they? So about the trade-offs between various different aspects of a particular structure.
Yeah, I mean, the sort of quick answer is you look at embodied energy, for example. We commonly now compare schemes using a plugin to give us an embodied energy output.
Is that Ladybird? Is it?
We use we use bits of our own stuff, and we use the iStructure spreadsheet as well.
Oh wow! Okay, fantastic. That's it's a nice little plug for that.
Yeah, no, it's great. No, I talked about that, a bridge which could be the lowest embodied energy, blah blah blah, but that uses the iStructure's with a spreadsheet plus our own stuff to try and prove that. So, I mean, one of the ways you could check would be embodied energy, volume of material, and I suppose metrics such as different shapes giving you least deflection. For example, if you take a form of a work of art and you're not quite sure if you tweak it here, you tweak it there, how that will affect the deflection, for example. So you could say by small tweaks could produce the least deflection then plugs back into the least material. So if you choose the option which deflects the least, in theory, it's the option which needs the less material to meet a certain criteria. So there are many criteria, and there are many ways of judging these things. Volume, CO2, technical criteria, minimum energy, minimum deflection. But you have to be kind of careful. And one of the tricky things of setting these computer scripts up is you have to, I suppose, pre-impose your criteria. So you pre-impose what you think the selection criteria could be, and you pre-impose what the parameters could be within which you work. But there's no guarantee, actually, they're the best parameters, and there's no guarantee it's the best selection criteria. So there's a word of warning there. But I suppose, again, it comes down to engineering judgment and engineering logic and engineering experience. You're choosing things which can be buildable, which are logical and have least material. So I don't want to give the impression we blindly choose, that one. The computer says that one, so we'll have that one. That's not the case.
It's an interesting thing that you mentioned deflection, actually, because with regards to the tensegrity cantilever, for example, the construction process of something like that would presumably induce some increasing deflection as you go along. Do you model those? Do you model that on like a staged sort of basis?
Yeah, no, we absolutely did. So the entire thing was modeled in one Grasshopper script using the the K2E plugins that we developed to do lightweight structures, because they deal with pre-stressed structures very well. They deal with very bent active lightweight structures very well. So we analyzed the entire thing, and then we analyzed chunks of it exactly the way you described. If you build this bit, how much does it move? If you add this bit, how much more does it move? And if you hang this bit by the crane, how much is the bit being hung by the crane moves? So yeah, we did a lot of work on that in the end, actually.
So you ended up sort of presumably adjusting the lengths of the cables in order to mitigate that deflection and make sure it doesn't droop all the way down to the ground at the end.
Yes. absolutely. And I mean, the story behind that was it went out the window in the end, because he did this fantastic staged analysis, stage simulation, and when they came to actually build it, they just couldn't build it because it was literally just empty space, cable, tube. Does the cable go in front of the tube, or the tube in front of the cable? And then you got the next one. So it was only by taking the augmented reality system to site and then looking at the where it was supposed to be in fresh air that was actually able to be built.
Okay, well, thank you very much. I think we're going to have to draw to a close there, unfortunately. I will just thank you very much, Stephen. And I'm sure there are plenty of more questions, but I think we could probably go all evening at this point if that were the case. Wonderful talk, and it will be it has been recorded and will be available on the website in the next couple of weeks. Thank you again, Stephen, and I hope to see you again soon. I have got just one or two slides before we close, and I shall share those now. So you're more than welcome to drop off camera, Stephen. And I shall do the same. There we are. Right. Thank you for watching. Please take the survey you'll receive in your inbox just after this concludes. It allows us to bring the content that you like, bring you more content that you like, apologies, and hopefully push forward some of the institutions' content so that it can be better tailored to what the direction the industry is moving in. Again, the recording will be available in the next couple of weeks. There are a few upcoming events which you may be interested in off the back of this talk. There's a mass timber lecture on the 22nd of March, based around the Anthony Timberland Centre. So if you've really enjoyed some of the timber stuff today, then you might want to jump onto that and sign up. Details are on the website. Young Researchers Conference is also on the 23rd of March. Perhaps some of the talks there may interest you as a result of some of this sort of cutting edge work that Stephen's shown today. The Designing for the Future Now e-conference on the 29th to the 30th of March. Again, very much future oriented with regards to sort of digital tools and sort of rediscovering some of the older forms of structures in sort of bending actives, and the Robert Mayer and the Fry Otto type things, Nervi as well, of course. And in terms of, I suppose, the analysis link is really the efficient design of tall buildings as a webinar. If you're interested in reducing carbon, efficient design of tall buildings is something we're going to need in the future as well. So that's on the 19th of April. And with that, I believe that's my final slide. Thank you for watching, and have a good morning, evening, or afternoon. Thank you.